Welcome to section 13.1. In this section, we're going to be looking at the concept of vector functions and space curves. So everything we've done with vectors up until now pretty much has involved vectors with numbers inside of them, but we haven't really talked too much about what happens if you want to put a variable inside of a vector. And that is definitely something that we can do and that we use quite frequently. So let's take a look at this first definition here. So a vector-valued function, also called just a vector function, is simply a function whose domain is a set of real numbers and whose range is a set of vectors. So we have r of t is component vector here, f of t, g of t, h of t. Or in the standard basis form, you have f of ti plus g of tj plus h of tk. Okay, so it's a function whose domain is a set of real numbers. So you input real numbers, that's t, and the range is a set of vectors. So for every t value, every number we put in, we get out a vector, and then another, depending on how many values of t we want to check. So like for this example right here, r of t equals t cubed, ln of 3 minus t, and radical t. So we have our component functions, right? So this is f of t right here is t cubed, g of t is ln of 3 minus t, and h of t is radical t. If we were looking for the domain of this vector-valued function, we would look at any domain restrictions, just like you do in algebra. We would see for t cubed, there are no domain restrictions there. T can be anything. The natural log, you cannot input a negative number into a natural log, nor can you put in 0. So it has to be greater than 0. So this right here, so t, in order for it to be, let me rewrite this here. So 3 minus t has to be greater than 0, which means that t must be less than 3. That's what this one is telling us. And then the square root, that's the more traditional one. We know that t has to be greater than or equal to 0 because you can't have a negative inside of a square root. So if we combine the domain restrictions, we end up getting this interval of 0 to 3, inclusive of 0, exclusive of 3. So this would be the domain of this vector-valued function. You can substitute in any real number on this interval into here to get out a vector. Anything outside of this interval would not give you a valid solution in the range. When it comes to working with vector functions, they very much behave like we would want them to. So we're going to just kind of dip our toe a little bit into the calculus aspect of things here. So if we wanted to take the limit of a vector-valued function of f of t, g of t, h of t, as t approaches a, all we would need to do is exactly what we would want to do. Take the limit of each component separately. So we get limit as t approaches a of f of t, limit as t approaches a of g of t, and limit as t approaches a of h of t. So if we had an example like this one that said find the limit of this vector function r of t as t approaches 0 of this, we would get, so limit t approaches 0 of r of t. That is limit as t approaches 0 of 1 plus t cubed, and that's I, plus limit as t approaches 0 of t e to the negative t j plus limit as t approaches 0 of sine of t over t. Okay. And then just compute the limits separately. So for this first one, as t goes to 0, this goes to 1. So we have 1i, or just I. For the j component, this goes to, that's 0. That e to the 0 is just 1. So you get just 0 for that one. So 0j. And the last one, as t approaches 0 of sine of t over t. This is kind of a special limit that you learn in Calc 1, usually once. So that would be if t is approaching 0 and the input of the sine matches the denominator like this limit goes to 1. So we end up getting 1k, or just k. So we end up with I plus k is the value of that limit. Okay, so this vector function, as t approaches 0, this vector function approaches this vector. So it starts kind of lining up into place. So it's like over here, and then as t gets closer and closer to 0, it's going to start getting closer and closer to that vector in question. Now, if we're using limits, we can also talk continuity. So a vector r is continuous at a value a if the limit as t approaches a of r of t equals r of a. So very similar to the definition in Calc 1, right? If the limit exists, the function exists, and they're equal. That is the condition for continuity. It's the same thing here with vector functions, so they're defined very similarly. Now, suppose that f, g, and h are continuous on an interval I. Then the set C of all points x, y, z in space, where x, y, and z are all functions of t, and t varies throughout the interval I, this set of points, which we're calling C, is called a space curve. So a space curve, and this is again a collection of all these points, as t, which is the parameter, t is the parameter in the parametric equations of C. As t changes, we get different values going into these functions. That plots a new point, right? So like when t is 0, we plot a point. When t is 1, we plot a point. When t is 100, we plot a point. And if you plot enough of those points, you will eventually have created a space curve, right? We don't know exactly what it would look like, but you will plot a space curve. Another way of visualizing this, given right down here. So think of C as a particle moving whose position at time t is f of t, g of t, h of t. So you can see here I've got my space curve that's giving kind of the trajectory that the particle is moving. And then we have the vector function r of t that is pointing at p. So then as t changes, that would move to, here. And then t changes again, and it moves to here. And it keeps going and going and going. And if you trace out enough, eventually you get the entire space curve. But particle motion is definitely one use of these space curves. So now that we have things can move in 3D. So let's take a look at this curve right here. So describe the curve defined by this vector function. R of t is 1 plus t, 2 plus 5t, negative 1 plus 6t. This one, and you might be looking at it thinking, well, how am I supposed to know? Well, this one actually should look hopefully familiar or similar to things that we have encountered already. Let me go ahead and break this into the components, into like the parametric form. We get x equals 1 plus t, y equals 2 plus 5t, and z equals -1 plus 6t. And this might make it a little easier to see, but this is the equation of a line, right? This is the vector equation. This is the parametric equations of the line. So this is a line. And we know a couple things about the line because we know these values come from a point, right? That starting point, that initial point. And the coefficients on the t's come from the direction vector, right? Position vector, direction vector. So this is a line passing through the point 1, 2, -1, parallel to the vector 1, 5, 6. Right, so we have already been working with space curves a little bit, but we're going to be able to kind of widen our search in space curves moving forward. So let's take a look at this example. Sketch the curve whose vector equation is r of t equals cosine of ti plus sine of tj plus tk. All right, so let's go ahead and break this into the parametric form. That's usually pretty helpful to kind of break it up component by component. So we have x is cosine of t, y is sine of t, z is t. All right, now we need to try to recognize a pattern or recognize something that we've worked with before. And we have actually worked with this before. Well, we haven't in here, but you should have worked with something like this before in Calc 2 when you learn parametric equations and like polar coordinates. This pair, x equals cosine of t and y equals sine of t, these parametric equations, these represent a circle of radius 1 centered at the origin. In other words, it's the unit circle, right? This is the unit circle. We can also show that that's the unit circle. I should say these represent a circle of radius 1 centered at the origin when z equals 0. That's mainly because we're working with a 2D sketch at the moment. But if we take this and we go x squared plus y squared, that's going to give us cosine squared t plus sine squared t. And sine squared plus cosine squared is 1. So we end up getting the equation x squared plus y squared equals 1. Which again, this is the equation of the unit circle. So now, if those were the only two equations, right, we would get here's x, here's y, circle of radius 1 everywhere. And this would be our curve. It would just be the unit circle. However, we're in 3D, and z is also a factor here. So we need to think about what's happening. So in the x and y directions, x and y are tracing out a circle. So they're just going around and around and around and around. They're tracing out the unit circle over and over and over again until we tell them to stop. So this is what's happening on x and y. Now, what z is doing, z equals t, and t is our parameter. So what this means, so since z equals t, as t increases, z increases steadily with it. So instead of having this circle being traced out over and over and over again, as t increases, we're tracing out the circle, but z is also going up. So we're tracing out the circle and increasing at the same time. And that ends up giving us kind of this spiral shape, or a helix shape is a little more accurate. So this causes the curve to spiral. So if we started like here at the point 1, 0, 0, we would trace the circle and it would start climbing as we went up. So you're getting kind of like a spring shape, and it'll keep going like that. And different points along here, like if we took like this point, which is right above the y-axis, this would be the point 0, 1, pi over 2. Because if t is pi over 2, we get 0, 1, and pi over 2. So as we're moving around that unit circle, the values are increasing, right? If we get all the way around one full rotation, right, this would be 1, 0, 2 pi. I can make that look a little nicer. 1, 0, 2 pi. Up there, that would be one full rotation around the unit circle. And then just keeps going and going, because we didn't put any restrictions on what it could be. You know, we didn't say 0 to 2 pi. It could be anything. So, but this is the general shape that we get. So we get a circular helix, or a circular spiral. So we can draw different types of space curves, depending on what the parametric equations look like, or the vector equations. Let's take a look at a little bit of a different example. Find a vector function that represents the curve of intersection of the cylinder x squared plus y squared equals 1 and the plane y plus z equals 2. So as you can see here, I've got the plane and the cylinder already drawn. You can see that the plane cuts through the cylinder and it creates a curve. Now that curve is not a perfect circle. It is circular in nature in that it does have like the curve of the cylinder, but it's not exactly a circle because this is at an angle. So we end up with something that looks kind of like this. Kind of like that. Okay, where it's a little bit lower on that side than it is on this side. And we're trying to find the equation of this curve right here. So it's gonna be going around like that. All right, so we know that this curve of intersection lies on both the cylinder and the plane. That's the whole point, is that it's on both. So the cylinder will give us some information. So we know for the circular cylinder, it is circular, and it's a radius of 1. So we're going to get x equals cosine of t, y equals sine of t. And remember, that would give us in the plane a circle. In 3D, this gives us a cylinder. Okay? Because again, z is not specified here, so it can be anything. It just grows up. So x and y are given there, with t going from 0 to 2 pi, because we're just going once around the cylinder. Now from the plane, we have y plus z equals 2, We know what y is from the cylinder. Let's go ahead and put that in. So we're going to get sine of t plus z equals 2. So we get z equals 2 minus sine of t. And really, that kind of just gives us everything we need. So the parametric equations of C are going to be x equals cosine of t, y equals sine of t, and z equals 2 minus sine of t. So for the vector function, which is what it asked us for, so our vector function, r of t, is cosine of ti plus sine of tj plus 2 minus sine of tk. And this is our vector function for this curve of intersection. So this red curve, that is its vector function. That is how we describe its points. And you can look at the points kind of along the corners here, or on the edges, like in the x direction and the y direction. And if we were to actually plot those, so like pick different values of t that give us those, we would get 0, 1, 1 over here. This one would be 0, negative 1, 3. So opposite, 0, 1, 0, negative 1. And then the incline goes up there. This one in the front is 1, 0, 2. This one in the back is negative 1, 0, 2. So you can see it's moving around the circle, right? The unit circle, 1, 0, 0, 1, negative 1, 0, 0, negative 1. And then the z component, 2 minus sine of t, is going up and down. So it's oscillating as sine does, right? So it's going from 2 down to 1, up to 2, up to 3, down to 2, and then just back and forth and back and forth. And it would trace out that curve. And that is the vector function for that curve of intersection. This formula for the vector function that we have, everything is in terms of that parameter t. So we no longer have these equations of x, y, and z anymore. All of these equations got converted into one vector function in terms of only t. And this is what we like to do, especially in calculus in 3D, because we want everything as simple as possible. We want everything in context of one parameter, if we can, instead of in terms of 3 different variables. So this vector function is called the parametrization of the curve C. This is the parametrization of the curve C. In other words, putting the curve C in terms of the parameter. So we have parameterized it. And that is the parameterization. And that brings us to the end of section 13.1. When we continue in the upcoming sections, we're going to keep talking about vector functions and performing calculus on vector functions. So I will talk with you all very soon.